The most important object in our solar system is the Sun. It keeps the planets in orbit and is responsible for all life on Earth. Scientists and astronomers have studied the Sun for centuries, and now we can observe it in more detail than ever before. Join us as we learn more about our closest star. Our Sun formed from a vast cloud of dust and gas called a molecular cloud. About 4.6 billion years ago, a gravitational disturbance or other nearby supernova explosion caused the cloud to begin to collapse in on itself. As this happened, the cloud spun faster and faster, and a disk of gas and dust formed around the central mass. As the central mass grew denser and hotter, nuclear fusion reactions ignited in its core. This process, which fuses hydrogen into helium, releases an enormous amount of energy and creates the intense heat and light that we see as sunlight. The Sun has been shining this way for about 4.6 billion years and will continue to do so for about another 5 billion years or so. Our Sun is currently what is known as a yellow dwarf star, but over time it will slowly use up its hydrogen fuel and begin to burn helium in its core. This will cause the core to shrink and heat up, while the outer layers of the Sun will expand and cool. At that point, the Sun will be known as a red giant. The red giant phase will last for hundreds of millions of years, during which time the Sun will grow to about 100 times its current size. It will therefore consume the inner planets, swallowing up the Earth, and eventually the Sun will run out of fuel and begin to collapse in on itself, releasing a tremendous amount of energy in what we call a supernova explosion. The core of the Sun will become a dense, compact object called a white dwarf. It will then slowly cool further over billions and billions of years until it fades away into a cold, dark object that we call a black dwarf. Now, what's interesting about this is our Sun can only produce elements up to the element iron on the periodic table. When it undergoes a supernova explosion in the far future, elements heavier than iron can be produced. So what's fascinating about this is when you look around and see any elements heavier than iron around you in the environment, or even elements inside of your body, anything heavier than iron must have come from another star before our Sun that underwent a supernova explosion. We truly are made of the same stuff that makes up stars. This process is known as supernova nucleosynthesis. During this process, temperatures and pressure become high enough to allow for the fusion of heavier nuclei. Neutrons are also released during the supernova explosion, which can combine with atomic nuclei to create the heavier elements. The elements produced through this process include the elements up to and including uranium. The second process is called neutron capture. This process involves the absorption of neutrons by atomic nuclei. Neutrons can be released during an astrophysical event such as a supernova and can then be captured by other atomic nuclei. The atomic nucleus can then undergo what we call beta decay, which converts one of its neutrons into a proton and thus creates a new, heavier element on the periodic table. This process is called the R process, which stands for Rapid Neutron Capture Process, and it's responsible for creating the heaviest elements in the periodic table, such as gold and platinum. The Sun has a diameter of about 1.4 million kilometers. This is an absolutely mind-boggling size compared to the Earth. This makes its diameter about 109 times the size of the Earth's, and its volume is more than 1 million times the size of the Earth. At its core, the Sun's temperature is 15 million degrees Celsius, but it's not just a uniform ball of fire. Rather, the Sun is best described as a spherical ball of plasma. It has layers, each with its own unique property. The first layer is called the core in the center of the Sun. The Sun produces the energy through nuclear fusions in its reactions in the core, which create heat and high-energy photons of light, which we call gamma rays. Above the core is what we call the radiative zone of the Sun, where the energy generated in the core makes its way to the surface through a process called radiation. The gamma rays produced by the core are constantly being absorbed and re-emitted by the plasma inside of the sun, gradually losing energy and turning from gamma rays into a lower energy photon such as visible light or infrared light. This process is known as radiative transfer. One amazing fact about the sun is that it can take a photon up to 1,000,000 years to complete this process. Stop and think about that. A photon of gamma radiation in the center of the sun can take up to 1,000,000 years because of being absorbed and re-emitted to make its way from the core to the surface of the sun to be emitted into space. Once the photon makes it to space, it only takes about 8 minutes to reach the Earth. The next layer is called the convective zone, where the energy from the core finally reaches the surface of the sun. Here, hot gases rise and cooler gases sink. This creates a turbulent, churning motion that helps distribute the heat and energy. Finally, the outermost layer of the sun is called the photosphere, which is visible to us here on Earth as the sun's bright and glowing surface. The temperature here is much cooler than that of the core at only 5,500 degrees Celsius. Once the energy reaches the sun's outer layers, it's primarily carried by photons that travel through space as electromagnetic waves. These photons move through the sun's atmosphere and are eventually released into space as sunlight. The sun's radiation has a broad spectrum, which includes ultraviolet, visible, and infrared light, as well as X-rays and gamma rays. This radiation can have a significant impact on Earth's climate and can be harmful to living organisms, which is why the Earth's atmosphere and magnetic field protect us from the most harmful of the sun's radiation. The sun also has a magnetic field that extends far into space with a north and a south pole just like the Earth. But unlike the Earth's relatively stable magnetic field, the sun's magnetic field is in a constant state of flux and motion, and the poles shift and change over time. The sun's magnetic field is generated by the motion of charged particles within its interior. It's thought to be generated by a dynamo process similar to the one that drives the Earth's magnetic field, but on a much larger scale. The dynamo is driven by the convection of plasma within the sun, causing charged particles to move and generate the magnetic field. The turbulent nature of the sun's magnetic field can include changes in the strength of the magnetic field itself, the number and location of sunspots on the surface of the sun, which we'll discuss in a few moments, and even the polarity of the magnetic field. The polarity of the sun's magnetic field flips approximately every 11 years in a process known as the solar cycle. During this time, the magnetic field gets weaker and weaker, and the sunspots become less and less frequent. The magnetic field then gradually strengthens again and reverses direction entirely, changing the polarity on the sun's north and south pole. The sun's magnetic field has been observed to flip about 22 times since the 1700s, when accurate observations began. The exact mechanism for the solar magnetic field reversal is not fully understood. It's thought to be related to the motion of the plasma in the sun's interior. As the plasma flows and rotates, it can cause the magnetic field lines to become entangled and eventually reorganize, leading to a reversal in polarity. The sun rotates on its axis, completing one rotation about every 27.3 days. But because it's made of gases, different parts of it rotate at different speeds. The equator rotates faster than the poles, completing each rotation in 24 days as compared to about 30 days. The sun also exhibits some fascinating phenomena that scientists have been studying for centuries. One of the most visible of these phenomena is sunspots. Sunspots are dark, cooler areas on the surface of the sun that are caused by magnetic activity. They often appear in pairs, with one spot having a north magnetic polarity and the other spot having a south magnetic polarity. Sunspots typically appear as dark, circular, or elliptical patches on the sun's surface with a darker center and a lighter border. Sunspots come and go during the solar cycle that lasts roughly 11 years, and their number and distribution varies over time. There are fewer sunspots right at the beginning of a solar cycle, and there are a maximum number of sunspots in the middle of the solar cycle. They're caused by the interaction between the sun's magnetic field and the convective motion of the plasma within the sun's outer layers. The magnetic field lines on the sun's surface can become twisted and tangled due to the rotation of the sun, and this can cause regions where the magnetic field is particularly strong. The magnetic field in the region exhibits a flow of plasma and causes the plasma there to be cooler. This cooler temperature causes the plasma in the sunspot to be darker than the surrounding plasma. So if you ever look at images from the sun and see sunspots on the surface, those are cooler areas of the sun's surface. Another fascinating feature of the sun is its dust rings. These are thin, donut-shaped rings of dust that orbit the sun. The dust rings in these regions come from comets and other small bodies of the solar system that have been vaporized by the sun's heat. The rings are faint and difficult to observe, but they can be detected using telescopes that are sensitive to infrared radiation. The sun's gravity is another fascinating aspect of the star. It's partially responsible for the tides on the Earth along with the lunar gravity, and it has profound effects on the orbits of the comets and other small bodies in the solar system. In fact, the sun's gravity is about 27.9 times that of the Earth's gravity. This means that if a person weighs 150 pounds on the Earth, he or she would weigh 4,185 pounds on the sun. The sun's gravity also has a great effect on its shape. The sun is actually not a perfect sphere. Its equator bulges out slightly, making it more of an oblate spheroid. This is due to the forces present during the rotation of the sun, which make the equator bulge out and the poles to flatten just a bit. Despite this, the difference is only about 10 kilometers, making the sun one of the closest naturally observable objects to a perfect sphere known. The sun is not only responsible for providing heat and light to the Earth, but it also emits a constant stream of charged particle which is known as the solar wind. The solar wind is made up of high-energy electrons and protons that are constantly streaming out from the sun in all directions at speeds of approaching 1 million miles per hour. The solar wind interacts with the Earth's magnetic field and creates a region called the magnetosphere, which protects us from the harmful effects of the solar wind. When the charged particles in the solar wind reach the Earth's atmosphere, they interact with the gases in the upper atmosphere, such as nitrogen and oxygen. This interaction excites the atoms and molecules, causing them to emit light at different wavelengths, which we see on the ground as colorful displays of the Aurora Borealis and Aurora Australis. The Aurora Borealis, which is also known as the Northern Lights, is visible in the Northern Hemisphere, while the Aurora Australis, or Southern Lights, can be seen in the Southern Hemisphere. The colors and patterns of the auroras depend on the type of gases present in the Earth's atmosphere, as well as the energy and direction of the charged particles of the solar wind. The auroras are most commonly seen in high-latitude regions such as Alaska, Canada, Scandinavia, and Antarctica, and they are more likely to be visible during periods of high solar activity, such as during the peak of the solar cycle. The first written records of the auroras date back to the ancient Chinese and Greek astronomers who described the phenomena as colorful lights in the sky. The Inuit people of North America and other indigenous populations around the world have long associated the auroras with spiritual or supernatural powers. They have given them names such as Dance of the Spirits or the Fires of their Ancestors. In 1619, the French astronomer Pierre Gassendi became the first person to provide a scientific explanation for the auroras. He suggested that they were caused by the Earth's magnetic field interacting with the particles emitted by the sun. Later, in the 18th and 19th centuries, scientists such as Edmund Halley, Benjamin Franklin, and Christian Birkeland conducted extensive studies of the auroras and developed a more sophisticated theory about their cause. Sometimes the sun can even emit highly energetic bursts of radiation and charged particles, which we call solar flares. Solar flares are the most powerful explosions in the solar system, releasing energy equivalent to millions of atomic bombs with each flare. They're caused by the sudden release of magnetic energy that has built up in the sun's atmosphere. When this energy is released, it heats up the plasma in the sun's atmosphere to millions of degrees Celsius, causing it to glow brightly and emit a burst of radiation and charged particles. Historical solar flares have been known to have significant impacts on the Earth. One such event was called the Carrington event. The Carrington event was a powerful solar storm that occurred on September 1st and 2nd of the year 1859. It's named after the British astronomer Richard Carrington, who observed the event and provided the first detailed account of its effects. The Carrington event began with a solar flare. The flare was so intense that it was visible to the naked eye, and Carrington and other astronomers observed it through telescopes. Within hours of the flare, a massive cloud of charged particles called a coronal mass ejection, or CME, was ejected from the Sun's atmosphere and headed directly towards the Earth. The CME reached the Earth in about 17 hours, which is an unusually short period of time for a coronal mass ejection to travel from the Sun to the Earth. The impact of the CME on the Earth's magnetic field caused a severe geomagnetic storm, which is a disturbance in the Earth's magnetic field that can have a range of effects. The most visible effect of the Carrington event was a spectacular display of the auroras, visible all the way down south in the Caribbean, Central America, and Hawaii. These auroras were so bright that people in the streets of cities like Boston and New York could read by their light. But the Carrington event had other effects as well. The storm caused widespread disruption to telegraph systems, which were the most advanced form of communication at the time. Telegraph lines sparked and burned, and telegraph operators received electric shocks, and some systems continued to operate even after the batteries were disconnected. On a few occasions, telegraph systems were able to transmit messages without a power source, as the electromagnetic energy from the storm was sufficient to power the transmission. The Carrington event was the most powerful solar storm ever recorded, and it's estimated that if a similar event were to happen today, it could cause widespread disruption to modern technology, including satellites, power grids, and communication systems. The event is often cited as a cautionary example of the potential impact of space weather on modern society. Another significant solar event was the solar storm of 1989. The solar storm of 1989, which was also known as the Quebec blackout, was a severe space weather event that occurred on March 13, 1989. It was caused by a powerful coronal mass ejection that was ejected from the Sun's atmosphere a few days earlier. The CME traveled through space and reached Earth, interacting with the planet's magnetic field, causing a geomagnetic storm. The storm was so severe that it caused widespread power outage in Quebec, Canada, and affected other parts of North America as well. The storm began on March 10, 1989, when a large sunspot region on the Sun's surface produced a strong solar flare. The flare was accompanied by a CME that was aimed directly at the Earth. The coronal mass ejection reached the Earth on March 13th and caused a major disruption to the planet's magnetic field. The geomagnetic storm caused by the CME resulted in a surge of electric current in the power grid of Quebec, Canada. The sudden increase in the electric current caused protective relays to trip, which shut down power to millions of people in the province. The blackout lasted for about 9 hours, and power was gradually restored as the effects of the storm subsided. The solar storm of 1989 also caused disruption to radio communications and satellite systems. Some satellites were damaged by the intense radiation from the storm, and communications with spacecraft were temporarily lost. The solar storm of 1989 was not as powerful as the Carrington event of 1859, but it was significant in that it demonstrated the potential impact of space weather on modern technology. It led to increased awareness and research into space weather, and measures were taken to improve the resilience of power grids and other critical infrastructure to space weather events. In recent years, scientists have launched many spacecraft to study the Sun up close and to gather more information about its properties and phenomena. Two such spacecraft are the Parker Solar Probe and the Solar Orbiter. The Parker Solar Probe, which was launched by NASA in 2018, is on a mission to fly through the Sun's atmosphere and study its magnetic fields, plasma, and energetic particles. The spacecraft is named after the late astrophysicist Eugene Parker, who first proposed the existence of the solar wind in the 1950s. It's about the size of a small compact car and was launched in August of 2018. Using the gravity of Venus, the Parker Solar Probe will do 7 flybys of the Sun, eventually getting close enough to be within Mercury's orbit. While Earth is about 93 million miles away from the Sun, the Parker Solar Probe will get as close as 3.8 million miles. To withstand the extreme temperatures, the probe is protected by a 4.5-inch carbon composite shield. This protects the probe even in an environment where the temperature can reach 2,500 degrees Fahrenheit. On the Parker Solar Probe, there are 4 instrument panels, each of which have a specific purpose. The Fields panel measures electric and magnetic fields within the Sun and hopes to understand the mechanisms by which the magnetic field aligns. The Whisper panel is the imaging mechanism in the probe. It can take images of things like coronal mass ejections and the solar wind. The Sweep panel can count the particles emitted from the Sun, like electrons and helium ions. It can also measure things like temperature and velocity in order to help scientists better understand the solar wind. Finally, the ESIS panel further analyzes the particles to better understand their origins and how they move through space. The Parker Solar Probe has already made several close flybys of the Sun and has gathered unprecedented data about the Sun's atmosphere and the solar wind. In fact, it has flown through the Sun's outer atmosphere, and it's touted as the first spacecraft to actually, quote, touch the Sun. In addition to this work, the probe has captured amazing images of our solar system, including the first visible images of Venus's surface. The Solar Orbiter, launched by the European Space Agency in 2020, is also on a mission to study the Sun up close. The spacecraft is equipped with a suite of scientific instruments that will allow it to observe the Sun's surface, atmosphere, and magnetic fields in great detail. It will also study the solar wind and its effects on the Earth and other planets. The Solar Orbiter is equipped with 10 different instruments, including a high-resolution telescope. It also uses the gravity of Venus in order to stay in orbit and can move so fast that it can hover over a specific area of the Sun as it rotates. It has captured the first images of the Sun's north and south poles from high latitudes. To protect the orbiter from extreme heat, a special substance was created to coat it with. Called solar black, it is made from calcium phosphate and is a dark powder. In fact, because the coating is so dark, the solar orbiter was given the unofficial nickname Blackbird by the team working to build it. Together, the Parker Solar Probe and the Solar Orbiter are providing us with a wealth of new information about the Sun and its impact on the solar system. They're helping us to better understand the processes that govern the Sun's behavior and are providing insights into the origin and evolution of our solar system. Our Sun is a fascinating star that is ever-changing. People on Earth now know more about it than ever before, and our study of it will continue for years to come. From the nuclear process at its core to the solar flares that can affect us here on Earth, we will not only improve our lives, but will also further our understanding of the universe. Learn anything at mathandscience.com.